Okay, everyone, welcome back. Hope you had a good weekend. Any questions before I start? Any problems you want to go over from the homework?
I think I had a problem. Let me just find it real quick.
Okay. The last time we were doing L'Hopital's rule, very, very nice rule. And we had looked at a few examples, specifically when we were getting infinity over infinity or 0 over 0. And then we still have some more to deal with. I ended class with an example of when we would get something like infinity times 0.
I'm already caught up on the homework. I wanted to look back at 3.3 on number 25.
3.3, number 25.
I was following along with the video that
I can do that. So this is back in 3.3. Number 25. And it gives you y is equal to 5 raised to the negative 1 over x. Right? That's the one?
Yeah.
And they're asking you just for the derivative of this. So when we look at this, we have to realize that the base is a number and the exponent is some function of x. So that means we're going to be using the formula that we have for the derivative of a to the x. Or, you know what, last class I told you treat it like a to the u. The derivative of that should be itself, a to the u times natural log of a, but then chain rule says you have to multiply times the derivative of what was up in the exponent, so u prime. We do not use the power rule, right? We don't use this rule, okay? Because here the exponent is a number and the base is the variable. So we don't want to use this. So when I take the derivative, I'm going to just rewrite it, 5 to the negative 1 over x times the natural log of 5, because that's what the formula says. And then I still have to multiply it times the derivative of what was up here. So remember that negative 1 over x is the same as negative x to the negative 1. That means just bring the x up to the top as a negative exponent. And now you can take the derivative. So if we take derivative of this, it's the same as this derivative. So the negative 1 comes out front, hits the negative 1 that's already there, becomes positive 1. And then you subtract 1 from negative 1, you get negative 2. And that gives you, that's the same as 1 over x squared. So I can just put out here 1 over x squared. Does that make sense, Brian?
Yeah, I got, in the video I got lost to how you got 1 over x squared, but now that you show it here, I understand.
Okay, good. Anything else?
No, that's all I got. Thank you.
Okay. Okay, so going back to this cheat sheet that I gave everyone for what to do when you have certain limits, right? So the important thing is we're looking at these expressions that we get when we're taking a limit and we're getting 0 over 0, or we're taking a limit and getting infinity over infinity. These are all part of what I call my limit summary worksheet here. So our formula sheet. We have looked at the first two there in yellow, and that's what previous sections were about. And we did those limits, and they were sometimes hard. But now we know that we can use L'Hopital, right? For both of these, we can use L'Hopital. But it has to look like 0 over 0 or infinity over infinity. And I did a few examples of that in class last time. And then at the end of class, I gave you one example of this, where you get 0 times infinity. So the idea here is that you're taking a limit, okay? And whatever x is going to, who cares, just something. And you've got two expressions that are being multiplied. And one of them is getting really, really small and headed to 0. And the other one's getting really, really big and headed to infinity. and they're being multiplied. So you can't tell who wins, okay? One number is trying to get small, the other number is trying to get big. So it's like this tug of war. And in the problem I did last time, this was the actual problem, limit x goes to infinity of x times tangent of 1 over x. We saw that the x wants to get big, but the tangent of 1 over x wants to approach 0. And so we did something, and at the end of it all, we said that the answer was 1. So it's like neither one of them actually won, right? Like this one didn't get to become infinite, and this one didn't become 0. Together, they just kind of like compromised and became 1 when you took the limit. But the main technique, the main thing you have to take away from this is that anytime you see 0 times infinity in a limit, what you're going to do is you're going to take one of the two expressions and you're going to drop it down to the denominator. And then you rerun the limit and you should get infinity over infinity or 0 over 0. So I'm going to do it. I'm going to start class with another example of that so you can see it in action. And let me see which one I want to do here. Yeah, how about this one? Limit x approaches 0 from the right of sine of x times natural log of x. So the first thing you want to do is take a look at what happens if you try like direct substitution. So if we just try and plug 0 in, and notice we're approaching it from the right. I'll kind of point out why that's important in a second. But if we just try and put 0 into this, sine of 0 from pre-cal is 0, right? Because sine on the unit circle, sine of an angle is the y coordinate, and when you're at 0 degrees, you're right here to the right. Whoa. When you're at 0 degrees, you're pointed out to the right like this, and that's the point 1, 0, and so the y coordinate is 0. You should know that already. I'm just reminding you. That's why sine of 0 is 0. So we know that that sine part wants to go to 0, and now we need to see what happens to the natural log part. So to do this, natural log of 0, well, natural log of 0, if you get on your calculator, is undefined. Like you get an error. And the reason why it's undefined is because you have to go back and think about what the natural log function looks like. And we did this a couple of classes ago. We graphed the natural log function and it went like this. Do you remember that? That's what it did. And so you can see that as you approach 0, right, we're approaching 0 from the right-hand side. So as we move along this function towards an x value of 0, right, here's 0 on the x-axis. As we try and get closer to it from the right-hand side, our function starts to dive down to negative infinity, right? That's where it wants to go. Now, I mean, it never gets there, but the closer we get to 0, the further down it is. So that means that this thing wants to head to negative infinity. You all agree? So
Yeah.
Yeah, thank you, Daniel. Okay, so what this means is that this whole thing together, all of this, is headed towards 0 times negative infinity. And so you've got something that wants to get really small times something that wants to get really big, but big, when I say big, I mean big but negative, right? And this is the case that we are looking for, where we take one of them and drop it down. Okay, anytime you see 0 times infinity, or even if it's negative infinity, you're going to take one and drop it. So when I say you take one and drop it, here are the two options you would have. I'm going to show you both. One option I could do is I could take the natural log and leave it there, and then on the bottom, instead of writing the sine x on top, I can write 1 over sine x on the bottom. And that's just because this is the way fractions work. If I have natural log over 1 over sine, that would flip and the sign would come back up, wouldn't it? So it's the same expression algebraically. Do you all agree with that? The other option I have is to leave the sine up top and move the natural log down. Now, again, when I move it down, I have to write as 1 over natural log of x. Because again, that's the same thing. The natural log would flip up and you would get back the same thing. So which of these is going to be better? Let's see. Let's just think about what we would do. If we now applied L'Hopital's rule, well, you know what, before we apply L'Hopital's rule, let's show that we could now apply L'Hopital's rule. So let's try this limit again. Let's let x go to 0. Natural log of x, we just said that that goes to negative infinity, didn't we? Yes. But look at the bottom now. We have 1 over sine. So the numerator is fixed, right? And the denominator is headed to where? What's sine of 0?
0.
0. So we have the numerator is fixed over something that goes to 0. And if you go back and look at this sheet that we had, anytime we had fixed over something headed to 0, we're either going to be getting infinity, negative infinity, or one of these answers. But for us, it really isn't that relevant whether or not it's positive or negative. What's relevant to us is that the bottom is becoming infinite also. And so you have some sort of infinity over some sort of infinity. And that is when you can use L'Hopital. Does that make sense? Is that clear to everyone?
Yes.
Okay. Good.
Yes.
Thank you. Now let's look at the other one. Does the other one work the same way? Okay, well, this top sine of 0 is 0. We know that, right? Over, now let's look at the next one. 1 over natural log of x. Okay, well, if x goes to 0, don't we already know that this bottom is going to head to negative infinity? Right? So you have a fixed number over something, this is fixed, over something that is headed to negative infinity. And if we go back again and look at our sheet from stuff we've learned, anytime we have a fixed number, doesn't matter if it's positive or negative, over something that's becoming infinite, that goes to 0. So that would mean that the bottom of this also goes to 0. And again, we have something that we can use L'Hopital, either one. Do y'all see that? So now the question becomes, which one do we want to do? So we have to kind of contemplate which differentiation is preferable for us. So L'Hopital's rule works by taking the derivative of the top. So I would have to take derivative of that. And then I'd have to take the derivative of the bottom. So I'd take derivative of the yellow, and then derivative of the green. And I would just create a new fraction. So the derivative of natural log of x should be easy for us, right? That's just 1 over x. We've learned that a couple of classes ago. Now the derivative of 1 divided by sine, wouldn't you have to use quotient rule?
You can change it to cosecant, right?
Yeah, or we could change it to cosecant, because 1 over sine is cosecant, and then just take the derivative of cosecant. Do y'all agree?
Yeah,
Yes.
I was actually, yes, I was gonna ask that. I was gonna say, like, do I have to like write it like natural log x over 1 over x, or could I just have like left it? Because when I see that, I just kind of want to flip the 1 over sine x to the top, but then it would give us the same thing we have at the
Yeah,
beginning.
you don't want to flip it back up because then you'll be right back where you were. But you can rewrite this 1 over sine as cosecant on the bottom.
So
way-
that way it's not a fraction anymore.
That way you don't have to do quotient rule. But then you have to know what the derivative of cosecant x is. But we know that because we have those formulas, right?
Yes.
Okay, now compare that to the other one. Okay, on the other one, it would be easy to do derivative of sine of x. We all know that that's cosine of x, right? But if we did the derivative of the bottom, 1 over natural log, that would be quotient rule, and there's no way to get around it. You would have to do quotient rule there. Does that make sense?
So the
So,
only reason,
Go ahead.
so the only reason why we have to do quotient rule on the second one is because there isn't like, I guess, like a flip side, as in like the other one has a 1
Yeah.
over sine x, and that gives us cosecant. And then the other one, we have to do it because we can't turn it into anything else, right?
Yeah, 1 over natural log of x doesn't turn into something that we know the derivative of easily. So that in itself, that right there is going to make me not do that one. Now you could still do it, trust me. I mean, you could do the quotient rule and work it out, but right now I'm leaning towards the one on the left because I think the differentiation is going to be easier. So I'm going to rewrite the left-hand side. Actually, I'm going to get rid of that. I'll just make that a little smaller. Okay, so it was that one or that one, right? That was what we had. We're choosing this one. So limit x is approaching 0 from the right. Okay, natural log of x over, I'm going to rewrite the bottom as cosecant x. And now I'm ready. So here it comes. L'Hopital's rule. I like to do an L with a circle around it to let everyone know I'm about to do L'Hopital's rule. And then the derivative of the top, which is 1 over x. And now the derivative of the bottom. So what is the derivative of cosecant x? This is where you break out your formula sheet, right? If you don't know it.
Like cotangent
Negative.
something, I don't have my sheet.
Negative cosecant x, cotangent x.
Negative cosecant x,
Woo!
cotangent x. That's it.
Half
Right?
of it right.
Okay. Now at this point, okay, at this point, we have a little bit of an issue because if we let x go to 0 now, okay, like let's see what happens. If x goes to 0, where does the top go? So if x goes to 0, we have fixed over 0, which becomes infinite. Do y'all agree? And then you have to figure out what's happening on the bottom, but wait a minute, cosecant of x, that's the same as 1 over sine of x, right? Isn't it? Like cosecant of x, that's what that was right there.
Yeah.
What do we already know that goes to if you let x go to 0? We know it becomes infinite, right?
Mhm.
So the bottom looks like we're going to have infinity here. So it looks like we have on the bottom infinity times. Now we do need to figure out what that goes to. So what's cotangent of 0?
0.
Well, here's where I might go to my formula sheet. Because remember on our formula sheets, on our formula sheets, remember we have pictures of the trig functions, right? And here's cotangent, and here is where is 0?
1.57.
0 is right here on our graph. See, this is the graph of cotangent, right? So here's 0. So where is it headed as you approach 0 from the right? Where's the cotangent function headed?
Infinity.
Infinity, right? So we would need to at this point understand from our knowledge of cotangent that this part is also headed to infinity. So on the bottom we have infinity times infinity. What's infinity times infinity?
A bigger infinity.
Infinity, right? I mean, that's
Infinity.
a huge number, right? But do y'all see we still have infinity over infinity?
Yes.
Basically where we are still. So right now, it appears at this point that that did not help us, but could we do L'Hopital again?
Yes.
We could, but think about how bad it's going to be if I do L'Hopital again. Just think about how bad it's going to be. I have to take derivative of the top, which is going to be a little messy. That's kind of like the one we just did with Brian on the previous example. When it was 5 raised to the -1 over x, we'd have to do something like that
X
here.
to the -1.
Yeah, rewrite x to -1 and then do our power rule. But worse, if we do the derivative of the bottom, then we have to do a product rule. Do y'all see that we have a product here? So I'm really not wanting to do another L'Hopital. So here's what I'm going to do instead.
Are you gonna do the where if it's f over g, you're gonna say
What you went back on mute. I heard if it's f over g, and that's all I heard.
are you gonna set it so that oh, actually never mind. You're already writing it like it's something else. Never mind. I take it back.
Okay. Right. Isn't that what this is? 1 over x, then cosecant of x is 1 over sine of x, right? And then cotangent of x is cosine of x over sine of x. And now what I'm going to do is I'm going to flip both those fractions up. So it becomes sine x over -1 times sine x over cosine x. And that makes these go away. Do y'all see what I'm doing? I'm just flipping the bottom fractions up and multiplying by the reciprocal. You okay with that?
Yes.
Okay, I'm not doing any L'Hopital right now. I'm not doing any L'Hopital at all. Go ahead. I didn't hear. If someone said something, I didn't hear. Okay. Y'all with me? This is a tricky problem. So are y'all okay so far? Let's think about what happens here, okay? If x goes to 0 right now, sine of 0 is 0, sine of 0 is 0, x goes to 0, cosine of 0 is 1. Right? So on top we have 0 times 0, so the top's headed to 0. And on the bottom we have 0 times 1, which is headed to 0. So again, we could do L'Hopital now, right? Because we have 0 over 0. But I still don't want to do it because look, if I did derivative of top, wouldn't I have a product rule? And then the bottom I'd have another product rule. And I'm really trying to avoid product rules right now. So here's the big point. Here's the big like turning point in the problem right now. I want you to look at this part in yellow, sine x over cosine x. Is that a problem? When I take the limit, if this was the only thing in the problem right now, sine x over cosine x, if I took the limit here, I get 0 over 1. Is that a problem? Is that an indeterminate form? 0 divided by 1. No, I see Natalie saying no, right? It's not. 0 divided by 1 is 0. So that's not a problem. The problem is this piece. Because here I get 0 over 0, right? And that is an indeterminate form. So what I'd like to do right now is on the side here, I'd like to just ask myself, what happens as x goes to 0 of just that sine of x over x? And I'm ignoring the negative that's out here right now. I'm just looking at this yellow part. I mean, yellow, sorry, green part. That's 0 over 0, isn't it? But I could do L'Hopital on just that piece. And I get cosine of x over 1. And that gives me 1. So I do derivative of top and bottom. I get cosine of x over 1. And now I let x go to 0. Cosine of 0 is 1. 1 divided by 1 is 1. So what that tells me is that this limit, I'm going to just write it all down again. Heads to, let's see, that's -1 times, that heads where? Where's that going?
0 over 1. Or 0.
That's going, no, what did we just do over here? What's sine of x over x going to in the limit? 1, right? That's going to 1. And where's this going? We said that was the yellow part, right? Where's that headed? To just 0, right? 0 over 1. So what are all three of these multiplied together?
0.
0. So the limit is 0. Okay, let's go back and just kind of recap this because it's a little tricky. We started out with this. We had 0 times negative infinity. We said, okay, anytime we see that, we're going to take 1 and drop it down. We chose not to do this one because I didn't want to do the quotient rule over here. So we went with this one. We rewrote the 1 over sine as cosecant. We went ahead and did L'Hopital, so derivative of top and bottom. Once we were here, we realized we still had a problem because we were getting infinity over infinity. Instead of doing L'Hopital again, I rewrote everything. When I rewrote everything, we still had 0 over 0, and we could have done L'Hopital, but again, I avoided it because I didn't want to do quotient rule, or sorry, product rule. But then I realized that when you write it this way, this part goes to 0, which isn't a problem. This part by L'Hopital goes to 1, and then you don't have a problem anymore. You don't have 0 over 0, infinity over infinity. Okay? So then you just put them all together, you get 0. Go ahead.
So it's
Right.
because you have multiplication between them, you can break it apart and do L'Hopital.
Exactly. Yep. Because there's multiplication between everything, you can split a piece off and take the limit of that one piece if you like. Now, just for the sake of doing it, I'm going to go back to this, where we were at this negative sine x times sine x over x cosine x. And this is more just out of curiosity for my own sake. We said just a second ago that we know that this gives us 0 over 0, right? So we could have done L'Hopital. Let's try it. Let's just see what L'Hopital would have given us. So see if you can follow me on L'Hopital. I have to take derivative of the top, and I have a product rule. So derivative of negative sine x is negative cosine x times sine x plus the derivative of sine x, which is cosine x, times the first function, negative sine x. All of that over, now I have another product rule. So here's my product. So derivative of x is 1 times cosine x plus now the derivative cosine of x, which is negative sine of x, times the first function, which is x. So do y'all see that the top, it's like, I did like, here's f, here's g. I did an f prime g plus g prime f, and then on the bottom I have another f, another g, and I do f prime g plus g prime f. Do y'all see that? Okay, let's just see what would have happened right now if we let x go to 0. Okay, let's let x go to 0 now. And I'm going to move this down just a little bit so that we can do something here. Okay, so if I let x go to 0, this becomes -1 because cosine of 0 is 1, but then I have a negative out front. This sine of 0 is 0, so I'm multiplying those two together, plus cosine of 0, that's 1, times sine of 0 is 0, but then times negative, it's still 0. So on top, I get -1 times 0 plus 1 times 0. So all of that together is just 0, right? Let's see the bottom. Okay, what does that become? Cosine of 0 is
1.
1. Okay, so this is 1 times 1, that's 1. Plus, okay, sine of 0, 0 times 0, that should give us 0. So the bottom is what?
1.
1. So the top is 0 and the bottom is 1. And 0 over 1 is 0. So we get the same answer, don't we? So all I'm getting at here is that, look, I mean, there's like different paths that we could take that get us to the same result, right? So there is no like, you must do it this way, okay? Is that my audio doing that, or is that someone else?
Someone else.
All right, I'm gonna mute everyone because I can't tell who that is. That's weird, it's still happening. Okay, I think it was Danielle. But what do y'all think? Do y'all have any questions on this?
I have a question on the
Yeah.
left. Just took the L'Hopital's on just sine x over x.
Right here.
Yes, on the bottom, we just rewrote it as sine x over x again. Why not rewrite it as like the cosine x over 1? Or is that just like,
Wait, why not write this bottom?
oh,
Yes.
no, sorry. Like on the bottom, when you rewrote it, and then you show the like, okay, it went to -1, 1, 0 equals 0. Why not rewrite that sine x
Sorry.
over x as cosine of x over 1 to show like
Cosine of x over 1. I'm not sure where I'm looking. Are you looking on the left side or the right side?
I'm looking on the left side,
Okay.
and then that bottom part, yes, there.
Mhm.
Where it says sine x over x, why did you leave it like that instead of writing it as cosine of x over 1 to show that you took the like L'Hopital's of it?
Why didn't I rewrite this as cosine of x over 1? Is that what you
Yeah.
said?
Yeah, after you
Using-
taking L'Hopital's.
Oh, I didn't. Oh, I did it over here. Sorry, I did that over here. So I took the arrow over here. I said, hey, this right here after L'Hopital is cosine of x over 1, right? which means that the answer there, that limit is 1. So since I already showed that work, I'm just saying that's what the answer is going to be.
Oh, okay.
Yeah.
That's
You
fine.
could have, if you wanted to, you know, rewrite this with this here and then show the next step that it's 1. But since I showed it over here, I didn't feel a need to rewrite it, I guess.
Okay.
Okay, what do y'all think? Eh?
That was a tough one for sure.
Yeah, it's a little bit messy. Okay, let's look at a different type of problem, because when we look back at this sheet that we have, I've kind of like, we can kind of say now, like, check, like if we have 0 times infinity, we understand the basic idea of what we need to do. Pick one, drop it, 1 over it, right? And then go L'Hopital and see what happens. And who knows, it could get a little messy, but we at least have a technique for it. What we need to address now is what happens when we have infinity minus infinity. So you have a really big number minus a really big number. You can't tell who's going to win. All right, same thing. A lot of people think infinity minus infinity is 0. It's not. Infinity plus infinity is infinity. But when you subtract 2 infinities, you don't know which one's dominating the other one. So we'll start with a simple example, and then we'll just kind of build from there. Okay, so what about this? Limit x goes to infinity of x cubed minus x squared. So first thing, let's just talk about what's happening. If x gets really, really big, that becomes infinite. That becomes infinite, and we're subtracting them. And that's an indeterminate form. We can't tell what's going to happen. All right. Please do not put 0 as your answer on a test, because that'll get you 0 points, actually. So you have to recognize this is an indeterminate form. We have to do something. So one of the things you can do, you can try, is factoring. Okay, factoring sometimes can work. In this case, factoring does work, doesn't it? They both have an x squared. So if I pull an x squared, I'll be left with x minus 1. Right? Just pull x squared out of both of those. And now you have multiplication, don't you? And so if you let x go to infinity, infinity squared, that's going to become infinite, times now infinity minus 1. Well, that's still infinite, right? I mean, it's becoming infinitely big. So we have infinity times infinity. And now that we have something that's infinitely big times something that's infinitely big, that should be infinitely big, shouldn't it? 2 infinities multiplied. Now, if one of those was 0, we'd have a problem, but we don't. This is just going to be infinite. And so that's your answer. And it kind of makes sense if you think about it, because if you have something cubed, right, that's getting really big, and you're taking away something squared, cubing something makes it bigger than squaring it. So it's like the cubic function here dominates the squared function. This gets bigger faster than this one gets big. And so if you subtract this one, it's not going to, when x gets big enough, this is not going to have an impact on it as much. So this one dominates. That one was a lot better than the last one, right?
I like it better.
Yeah, that was easier. Okay, how about this? So can we first agree with infinity minus infinity?
Yes.
Yes. Okay, so we have to do something. So I told you factoring. Can you factor this?
Yeah.
Is there something they both have in common?
You can factor out square root of x, and square root is just half of the x.
Good, good. So you have to realize here that you can pull a square root of x out. And if I pull a square root of x out of here, I'm left with a 1. And then if I pull a square root of x out of this one, you have to understand that that would leave you with the square root of x. Now, why? Because if you distribute this back through, right, If you do square root of x times 1, you get this. And square root of x times square root of x, these square roots go away and you're left with x. Now, when you run the limit, this goes to infinity. Square root of infinity is still infinite. And this one is 1 minus, right? 1 minus something that's becoming infinitely big. That should give you negative infinity because you're taking it away from 1, so it's negative. And now when you multiply a huge positive number times a huge negative number, you should get a huge negative number. Is that okay?
So for here, you're just asking us to simplify the problem and find if it's infinite or negative infinity.
Well, that's what it's turning out to be, right? I mean, what I'm trying to get you to see right now is that if you see infinity minus infinity, one thing we can try is factoring, okay? And if we factor, a lot of times the factoring creates a product, right? That's what factoring is. It's turning a sum or difference into a product. Once you have a product, multiplying infinities together, you're going to be able to tell what the answer is. As long as they're both infinite, right? Then when you multiply them, you'll get something. You'll either get infinity or negative infinity.
Okay, I understand. Thank you.
Now let's try another one that might not be, some people I can guarantee you had a little bit of trouble with that one. What about this one? So this says that we want to take x, let it get huge, right? We want to cube it, and then we take the square root. So if you take infinity and cube it and take the square root, do you all agree that this is still going to be infinitely big?
Yes.
Okay, and then this one says take infinity and square it and then take the cube root. That's still infinitely big. And we're going to subtract those two. And that is an indeterminate form. Okay, so this is bad. This section here with these forms I'm showing you right now are all the situation where it's bad, right? 0 over 0, bad. Infinity over infinity, bad. 0 times infinity, bad. Infinity minus infinity, bad. But now we have L'Hopital, right? Notice we haven't used L'Hopital yet, have we, on any of these yet?
No.
Okay. But how about the factoring? Is it going to work? Can we factor here?
Can't you rewrite it first?
How? How do you want me to rewrite it?
I'm probably gonna say it wrong, but can't you put x 3 over 2?
Okay, good. We can rewrite this. These are called, so the form in yellow is called radical notation because you're using the radical symbol. But we're about to rewrite that as x to the 3/2 instead of as the radical. So this 3 is the power and the root is the denominator here. So the 3 comes from here and the 2 comes from the square root. So this is called rational exponents. So this is radical notation and these are rational exponents. Those are two things. You know, that's something you learn in like algebra, but normally you learn it before algebra. It's like a intermediate algebra, properties of exponents type class. If I do that, I can rewrite the other one as x to the 2/3. Okay, I don't know who suggested that. I just heard someone say it. And someone said, can you do that? I said, yes. So yes, you can do that. Now what?
Can you find the lowest common denominator of the exponents?
Okay, so I think what you're saying is look at the two fractions you have there, 3/2 and 2/3. And see if you can find a common denominator between these two.
Yeah, 6.
Yeah.
6, okay, so how could you rewrite this fraction having a 6 on the bottom instead? Wouldn't you have to multiply by 3 on the top and bottom?
Yeah, so 9 over 6.
9, 6. Okay, what about this one? If we wanted a 6 on the bottom here, we'd have to multiply top and bottom by 2, right?
Yeah, so 4
So we get
over 6.
4 over 6. Okay, so you're suggesting, and this is all correct, by the way, everyone. We are doing, this is going right. Who's saying this? I'm not sure who's saying this.
Benjamin.
Oh, Benjamin, there you are. Okay, Benjamin, good. So we're going to rewrite this as x to the 9 over 6 minus, and this one we're going to write as x to the 4 over 6. Okay. Now, here's the tricky part. If this hasn't been tricky enough, this is the tricky part. You've got to figure out what 9/6 and 4/6 has in common.
4/6.
4/6. They both have 4/6. So let me write it first, and then hopefully you'll see what's going on here. I'm going to factor out an x to the 4/6. Now, when I multiply this back through, I need to get this out, right? I need to get this. So look, I'm going to put a -1 at the end because I think that's the easiest one to see. If you do x to the 4/6 and you multiply it through here to a 1, you get back this, right?
Mm-hmm.
What would you need here, though, to get back x to the 9/6?
5/6.
5/6. Good. And that's because when you multiply x to the 4/6 times x to the 5/6, you add the exponents. And so this becomes x to the 9/6. You add the exponents, you don't multiply them. And so that's x to the 5/6. Now, why is this helpful? We've created a multiplication here, haven't we?
Yes.
And now I know that this, if x gets huge, that becomes huge, right? And I know that this over here becomes infinity minus 1, which is infinite. So we have infinity times infinity, which means that our answer is infinity.
So it's okay for our answer to be infinity?
I'm sorry, what? I didn't hear that.
All right, it's okay if our answer is infinity then, right? It doesn't
Yes.
have to be a number.
Yeah. Oh, yeah. You can have a limit that's infinite. That just means that this thing is tending off and getting bigger and bigger. Okay, one more example of this, then we're going to move on to the next one. Next idea. How about this one? Yeah, let's try this one. Limit x goes to infinity of x minus the natural log of x. Okay, x is going to infinity, so we know that that goes to infinity. Then natural log of infinity. So we need to figure out what this is doing. So that means you need to look at the natural log function. And we need to know what's happening as x becomes infinite. So what happens is we start moving to the right forever. We start moving along this function. Where's the y value going? It's
Forever.
going to infinity,
Positive.
right? Positive infinity. So we have infinity here. So we have infinity minus infinity, and that is an indeterminate form. Agreed?
Yes. Quick question.
Yes.
What if it said x to the infinity from going from the left, coming in from the left or something like that? Like it's asking us to get the limit as x approaches infinity from the left. Like what would that be like?
Well,
Or
you
is that even
can't
possible?
approach, you can approach positive infinity or you can approach negative infinity. You can never approach infinity from the left or from the right because infinity is not a number. So I would, you could never say like little plus above the infinity because you can't come into infinity from the right-hand side or from the left because it's not a number. Does that make sense?
Yes, sir.
Okay. All right. Do y'all see what is a problem right now? What's the problem?
Infinity minus infinity.
Yes, okay. But how is this different than anything we've done so far?
Yeah, really, like it's hard to can't factor.
You can't really factor out anything, right? Because you can't take this x out of the natural log. No, right? That's illegal because
constant,
it's trapped. It's in the argument. Yeah. But man, I'd really like to try and factor it. I really would. So let me try something. If I could pull an x out, I would have a 1 here, wouldn't I? Because x times 1, that'd give me x. But the only way I could factor out an x is if I could actually imagine that there's now an x being divided here. Now I know that that's weird, maybe the first time you've ever seen something like that, but I have factored an x out of both of these. This x came out, I'm left with a 1. Here there wasn't an x, but I factored an x out anyway, and I put this as 1 over, or I put this as natural log of x over x. Why is this working? Because if I distribute, I get back that. And if I distribute here, what happens to the x's?
They
They
cancel.
And I get back the natural log of x. So this is a clever little way of factoring that you can always pull something out as long as you divide by it. Let me give you another example, just so you can see this. 5x minus 3. Let's just go back to good old linear expression from college algebra. Can you factor a 5 out of both of these? Like back in college algebra, can you factor a 5 out? No, right? But couldn't I do this? 5x minus 3/5.
Yes.
Yeah, so if I distribute this back through here to here, I get a 5x. And then if I go here to here, the 5's cancel and I just get the -3. Now, does that help us? Let's see if that helps us. If x goes to infinity, this is infinite, isn't it? Y'all following me? Yeah. Okay, and then I have 1 minus. Now, what happens here? What is natural log of infinity? Where's that top part headed?
Infinity.
Infinity. So I have infinity right here. Over, where's the bottom part headed? Where's this green part headed?
Infinity.
also. So what is infinity over infinity?
Infinity
No,
or something.
0.
no. Infinity over infinity is,
A problem.
we don't know, right? We don't know what that is, do we? We don't know what that is. However, we can go figure it out. We can now make this our new problem over here. Say limit x goes to infinity of natural log of x over x. We know that that goes to infinity over infinity. And anytime we have infinity over infinity, we can use L'Hopital's rule, can't we?
Yes.
Yes.
So use L'Hopital on just this piece. What's the derivative of the top?
1/x.
1 over x over what's the derivative of the bottom?
1.
1.
Okay, so this is just the limit as x goes to infinity of 1 over x. And now if I let x go to infinity, I get 1 over infinity, and that goes to 0. So what is this telling me? This tells me that when I do this limit right here, this part goes to infinity. And then I have times 1 minus, and what did this part go to just now, we said?
0.
0.
And so I have infinity times 1, which is infinity. So the answer to this is infinity.
I have a question.
Huh?
Is the answer always going to be infinity for?
No.
Oh, okay.
I mean, whenever you have infinity minus infinity, then most of the time you get infinity. Most, but I can't say every time, okay? Most of the time it's either going to be infinity or negative infinity, one or the other, but not 100% of the time, unfortunately. Most of the problems that we're going to see in this class, it will be though. But you still have to show the work. You can't just like, you can't just start the problem and just like try and just guess. I think it's going to be infinity and then get it right because you guessed. You have to show some work to convince yourself and me what the answer is. Okay.
In Cal 2, is that when we're gonna encounter more of the the answer is not going to be infinity?
Well, in Cal 2, you're going to be facing limits again with infinity, x going to infinity, and other numbers. And you're going to be getting, in Cal 2, you'll be getting all these sorts of different indeterminate forms. So in Cal 2, you're going to need to know, like, oh, okay, I've got 0 times infinity. Oh, I remember what to do with that. Most of my Cal 2 students don't remember. Most of my Cal 2 students remember when they remember what to do with infinity over infinity and 0 over 0. They know how to use L'Hopital there, but they forget how to handle this, and this. Everything in blue, my Cal 2 students usually have to go and look it up again. And some students in my Cal 2 classes, for some reason or another, there's actually some people some professors who don't teach L'Hopital's rule. So some of my Cal 2 students, they have to go back and learn this on their own, which is kind of a nightmare, but
What?
yeah. Okay, you ready? We're moving on. Not to new material now. I just showed you this. We've done everything here. We still need to do these right here. All right, so 1 to the infinity, 0 to the 0, infinity to the 0. So I'm going to write them down first, just so you can see. 1 to the infinity, 0 to the 0, infinity to the 0. Let's talk about why these are indeterminate forms. Okay, because you need to understand why these are a problem. So imagine, let's just look at this one first. You have in the base, you have a number that says, I want to be 1. Okay, that's what's happening down here. This saying 1, I'm not saying the number 1, I'm saying I'm taking a limit of something and the base is trying to be 1. And then you have this exponent up here in the top that says, I want to be big. All right. So would we all agree that if you took the number 1 and raised it to any power, it'd still be 1, right?
Yes.
But what if it's close to 1 and not 1? So imagine this number is like 1.0001. And let's say I raise that to a number that wants to be big. So like 1, what's that? A million trillion? Is that a trillion? What if I take 1.0001 and raise it to the trillionth power? This is going to get bigger, isn't it?
But wouldn't that not be 1?
It's not, yeah, this is not 1, right? And I'm raising it to a big power. So look, the exponent, this part up top, the exponent is saying, hey, look, it's looking down on this guy and it's saying, hey, I want to make you bigger, right? I want to make you bigger. But the base is sitting here saying, wait a minute, talking back to that, saying, wait a minute, I really want to be 1. And if I could just somehow get to 1, then your power doesn't affect me anymore, right? If I'm the number 1. So it's like this tug of war. It's just like the 0 minus 0 is a tug of war. It's just like 0 divided by, just like infinity minus infinity is a tug of war. Just like 0 over 0 is kind of a battle. This is, again, a battle. It's an indeterminate form. Who wins, right? That's the question. Who wins this battle?
1.
Well, it depends on the problem, actually. Every problem is different. So let me show you. I'm going to show you one of these. And then you'll see how to do them. But before I show you, let's look at the next one. Why is that a problem?
Because exponent of 0 equals 1.
Yeah, so think about this. When the exponent of something is 0, anything raised to the 0 should be 1, right? Anything raised to the 0 should be 1. But 0 raised to any power should be 0. So it's, again, this battle. The base is sitting down here saying, hey, I really want to be 0. Please let me be 0. And the exponent's like, wait a minute. I don't care what you are. If I raise you to the 0, then you have to turn into a 1. And so this battle occurs. Danielle, your audio is really, really bad today. And I just hear that's what I'm hearing. Sorry, I'm just letting you know I'm not responding because I don't understand. Yeah, no, it's not working. Sorry. So the next one is infinity. Danielle, stop, please. Stop, please, Danielle. We can't understand you. So it's just really kind of
Danielle, just use the chat to type it in.
Yeah. Okay, so infinity to the 0. So think about this case. The base wants to become really big. Okay. Okay, sorry about that. So infinity to the 0, right? You have the base wants to become really, really big, 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 big. But again, the exponent's like, wait a minute, I want to be 0 and I should be able to turn anything into 1, right? So it's this struggle. Do y'all understand this or not? Does this kind of make sense?
Yes.
Yes.
Okay, do not confuse those forms with things like this. What if you had infinity raised to the infinity? Would that be a problem?
No.
No.
No, that's not a problem. The base wants to be big, right? And then the exponent's like, well, I'm here to help you, right? I'm going to make you big too. So that's not an indeterminate form. Something else. How about 1 raised to the 0? 1 raised to the 0.
Just
So
one.
base wants to be 1, right? And the exponent's like, hey, that's what I do. I turn people into 1, right? So they're like helping each other. That's not a problem. You could have, I'm trying to think of some others that could be, here's one, 0 to the infinity. That's a tricky one. The base is like, hey, I want to get really, really small, right? And the exponent says, I'm going to raise you to bigger and bigger powers. What happens when you take a small number and raise it to a big power? Does it get bigger or smaller?
Bigger.
Think about it. If let's say I take a number that's really small, how about like 1 over 100? And I raise that to a big number, like 100 power.
I'll get smaller.
This gets smaller, doesn't it?
Yeah.
If you take a small number and raise it to a big power, it gets smaller. So this wanting to become 0 and this saying, I'm going to raise you bigger powers, just helps accelerate that and makes it get to 0 faster. All I'm doing is trying to show you that these forms are not what we're interested in because these don't require any calculus, any limits, any L'Hopital. These are things we can't tell who wins. And so that's what we're interested in. And that's what the formula sheet tells us. Here are the 3 indeterminate forms to worry about, all right? Okay. Now, an example. And why don't we start off with the like foundational, fundamental, like awesome, most awesome limit that I'll probably ever show you. Limit x goes to infinity of 1 plus 1 over x raised to the x. I put stars next to this because you're going to probably be a little bit surprised when I tell you when we figure out what the answer is here. All right. So let's first figure out what the form is that we have. Do we all agree that that right there is headed to 0?
Yes.
Okay, now is it ever 0?
It should not be.
It should never be 0, but it'll be really close to 0, right? The bigger that x gets, the smaller this fraction gets,
Yeah.
right? Now, if I add that to 1, do you agree that that is going to be close to 1? Now, I mean, I cannot stress this enough to you. This is close to 1. Close, right? It's not 1 though, right? Because we're taking 1 and we're adding this little tiny little number, 1 over x. We're adding this little bit to it. So it's close to 1, but it's not 1. Agreed?
Mm.
And then we're raising it to a power that's becoming infinite. So this is 1 to the infinity, and that is an indeterminate form. So we don't know. This is bad. We need to do some algebra or some sort of trick or something, right? Any questions? So I'm going to start by rewriting the problem. And before I even go about trying to do this, before I even do anything with it, I just want to take you back one more time and talk about these indeterminate forms and what we've discussed you do. If you get 0 over 0, L'Hopital. Infinity over infinity, L'Hopital. 0 times infinity, take 1, drop it, then L'Hopital, right? Infinity minus infinity, try and factor. Yes, that's what we've discussed. Now, these 3 are all done the same way. All right, here's what you do. And it's going to seem very weird that I do this, but just follow me on this. We are going to call this y. Okay. Hold on a second. I need to do something. Let me see. I think Danielle's trying to get back in and she's not coming in. She can't come in. I got to figure out how to do this.
Professor Daniela just texted me. She said
I know. That's what I'm doing. I'm trying to let her back in.
no, actually, she said that she wasn't messing with her mic. It was just her computer.
Okay, whatever it was. I mean, I don't think she had any control anymore over the sound that was coming to us. So that's why I removed her, because I don't think she could stop it. Let me see. Hold on real quick. Sorry, everyone. Let me just see if I can't get her back in here real fast. Participants. While you're sitting there, I said, you can see that, right? Y equals that. The next step we're going to do is we're going to take the natural log on both sides of the equation. Oops. Well, I can't figure out how to let her back in. Oh, shit. Oops. I tried muting her and it wasn't working. Yeah, it says allow previously removed to come back in. Look, just so y'all see this, so that y'all can tell Danielle I was not being mean to her. I have a setting in here. Where is it? I just saw it. Here we go. I removed her. So see how it says allow removed participants to rejoin? It's on, right? So that she should be able to rejoin, but I'm not sure why she can't. Okay, we have to move on.
Again. Oh.
What's that?
For the rejoin option, there's a button that says reset. Maybe try that and then turn it back on.
Just try and reset it.
Yeah.
That's a good idea. Maybe she.
Hey, can anybody hear me?
That was like classic timing. Perfect. You couldn't have done that better. That was so awesome. Okay. Yeah, you're back. Yes. All right.
Yippee.
Yeah, you sound better now. Okay. All right. So everyone, you ready? Here we go. In those 3 cases that I boxed, I said they're done all the same way. We just say, hey, the limit we're looking for, we're just going to call it something. We're going to call it y. Okay. If you want to call it some other letter, call it some other letter. We're calling it y. And then what we're going to do is we're going to take the natural log on both sides of the equation. So we're going to do natural log here and natural log here. So now we have this natural log of y equals. Now, the cool thing about the natural log is that when you have a natural log, you can put it past the limit. Okay, you can push it into the limit. So we have limit, x goes to infinity, then the natural log, then 1 plus 1 over x, and then raised to the x. Why do you think we introduced a natural log kind of out of nowhere? Why do you think we did this? Elise, what did you say?
Because the exponent is x, maybe?
Okay, yeah, so isn't there a property of logs that we learned? Well, we learned it in college algebra, but I pointed it out to you a few times now, that if you have natural log of x to a power, the power can drop out front, right?
Yes.
So that's what I'm going to do. I'm going to use that property now, and I'm going to pop the x out to the front of the natural log. Now it becomes x times natural log of 1 plus 1 over x. Now we did something like this when we were doing something called logarithmic differentiation in one of the previous sections. This is not the same as logarithmic differentiation because we're not trying to find the derivative of a function. What we're trying to do is find a limit. And anytime we have one of these three forms that I showed you a second ago, we will always do this. Now, what did we gain from this? Well, let's see. Let's take the limit now. X goes to infinity. That goes to infinity, doesn't it? Times, now let's talk about this. Where does this go? 1 over infinity goes to 0, right? 0 plus 1 goes to 1. And what is the natural log of 1? With a drum roll in the background. What's natural log of 1? Natural log of 1 is 0. 0. 0.
Yay.
0. So this is headed where?
0.
To 0. And now look what we have. Infinity times 0, don't we? And that is now this now. We've now turned it into this problem. Do you see that? Started out as a 1 to the infinity. We did this natural log thing, and now what we've done is transformed it into the 0 times infinity problem. And now that we have the 0 times infinity problem, we just pick one of them and drop it to the denominator, as you know, just like we did to start the class off. So I'm going to write the left side. I'm continuing to write the left side down each time. So what am I going to put this over?
LNY?
No, I'm taking, I have to pick, right? I have this one,
Oh,
or I have
X.
this one. And I'm going to drop one of them. I decided to leave the natural log here, and I'm going to drop the x to the bottom. So it's going to come down on the bottom as a what?
1 over
One
x.
for x.
1 over x. Okay. Now, a quick check of this. If we just do a quick check to make sure we can use L'Hopital now, let's just see what happens. If I let x become infinite, 1 over infinity goes to 0. 0 plus 1 is 1. Natural log of 1 is 0. The top goes to 0. Bottom, 1 over infinity, fixed over infinity goes to 0. We have 0 over 0. Now we can apply L'Hopital's rule. So I continue. The natural log of y equals, by L'Hopital's rule, okay, I have to take derivative of the top. Okay, what is the derivative of natural log of anything?
1 over that anything.
1 over that anything. So it's 1 over 1 plus 1 over x. Okay, times, now I need to take derivative of what was inside the natural log. So the derivative of 1, 0, plus the derivative of 1 over x. We did that to start class, didn't we? Do I need to show that, or is everyone comfortable with the fact that that's negative 1 over x squared? Is everyone comfortable with the derivative of?
Yes, comfortable with that.
Yeah.
That's just the derivative of the top, right? All over the derivative of the bottom, but what's the derivative of the bottom? Negative 1 over x squared again, right? And lucky for us, these cancel. So here's where we are. The natural log of y, which is the left side, equals the limit as x goes to infinity of the only thing that's left there, which is 1 over 1 plus 1 over x. Yes? Let x go to infinity now. If x goes to infinity, where does that go? 0. And so we have 1 over 1 plus 0. It's 1 over 1 plus 0.
One.
It's 1, right? So here's where we are. We're almost there. The natural log of y equals 1. So when we do this limit now, this goes to 1. We have that the natural log of y equals 1. So remember, what was it that we were trying to find? Way up here, we were trying to find this limit right here, right? And we called this thing y, didn't we? We said, hey, let's just call this limit y. And I told you, just do it and you'll see why. So we called it y. And now here's what we know. We don't know what y is, but we know that the natural log of y is 1. To get y by itself, what I do is I come in with the inverse function of natural log. The inverse function of natural log is e. So I apply e to the left side and I apply e to the right side of the equation. And I do that because e to the natural log, these kill each other off, and I'll be left with y equals, then the right-hand side becomes what? E. It's just e. E to the first power is e. So end of story is this. The end of the story is this. The limit as x goes to infinity of 1 plus 1 over x raised to the x is the number e.
Hey, it kind of looks like the interest equation, kind of, right?
It is, exactly. That's exactly where the interest equation comes from. The interest equation that Benjamin is referring to is when you look at like simple interest and how you calculate simple interest, it always involves e. And the reason it does is because of this limit. So this is a very, very profound result, because believe it or not, we just defined what e is. Like if someone were to, the way I like to think about this is this. Let me show you on a different page. There's a couple of important numbers that you've learned in math. Okay, pi is one of them, right? Pi is an important number. You've heard about it. It's used a lot. You know, if someone were to come up to you in like a dark alley, you know, you're walking, someone comes up to you in a dark alley and grabs you, throws you up against the wall. It's like, you know, what's pi, man? What's pi? You know, tell me what pi is. You'd be like, okay. Pi is just the circumference of a circle divided by its diameter. And they'd be like, okay, cool. You know, like there, you've defined it, right? Someone asks you what E is, right? Same thing. Tell me what E is, man. We now have a definition for it, which before you never did. You never had an easy way to explain what E is. Now we do. E is just the limit as x approaches infinity of 1 plus 1 over x raised to the x. That's the definition of E. So a lot of you have heard that E is approximately 2.718, right? Y'all heard that before? E is about 2.718. So one thing you could do to try and convince yourself of this, or to see that this formula we got is true, what would happen if we just take a really big number? Like, let's say we go with, I'm going to go with 10,000. That's not infinity, but what happens if I do 1 plus 1 over 10,000, and I raise that answer to the 10,000, and I do that on my calculator, okay? So I have to do everything in parentheses first. So I'm going to do 1 over 10,000 first. Then I'm going to add 1, and then raise that to the 10,000th power. And what I get is 2.718145927. If I took a bigger number, like instead of 10,000, if I did 1,000,000, 1 over 1,000,000, I get So imagine a million in there instead, 2.718280469. Now, what I can tell you is that this answer is more accurate than this answer. And if I want an even more accurate number, I'd use something other than a million. Maybe I'd use a trillion. And if I want it more accurate, I just go with bigger and bigger values of X. Does that make sense? If you could go to infinity, if you could, then that would be exactly what E is. And that's why E is what we call an irrational number. It just keeps on going on forever, never has a pattern to it. It's because you can never actually get the exact value. So at some point you have to plug a number in. What's that?
In our calculator, it's just an approximation for E.
Oh yeah, your calculator is always an approximation, always. Yep. Okay. So let's look at another one. I'm going to do this one a little faster because we've gone through one of these now. So what if we have limit how about this? X approaches 0 from the right of the square root of X raised to the X. I'm going to give you a minute or two to see if you can't follow the same process that I just showed you. I'll give you about 5 minutes, see how far you can get with this. Do y'all want to have the other one up at the same time?
That would be nice.
Yeah.
All right, let me put this one up here. I'm going to have to zoom out on it. That should be enough right there. And I'm going to paste that other one right here. So try and do that one using the same sort of procedure. And I'll give you 5 minutes. Okay, I've shown the work here. So if you're able to get this, good for you. I'll walk you through it quickly. So the first thing you have to do is realize that you have 0 to the 0. So when you take the limit as x approaches 0, you get 0 here, then you get 0 in the exponent. So 0 to 0 is bad. That's an indeterminate form. You can verify that off of your formula sheet. After you verified that, you realize that with one of those 3 forms, you have to bring in a y, then you have to take natural log on both sides. You can move the natural log past the limit. Once you get to this stage, you drop the x out in front, and now you have a product. You can check here, even though I didn't show it, that this goes to 0, and then natural log of 0 goes to -infinity. So at this point, you have the form where you can drop one of them down. So I decided to drop the x down as a 1/x. And now I'm set up and ready for L'Hopital. Any questions up to that point? Sure. Okay, so now L'Hopital, I take derivative of the top. So derivative of natural log of something is 1 over it, times derivative of what was in here, which is, well, derivative of square root of x, we've been through this many times, is 1 over 2 root x. And then derivative of the bottom, we kind of done that several times today. That's -1 over x squared. And even though this looks ugly, algebraically it cleans up because you can multiply straight across here. We'll get 1 on top, the 2 stays, you get root x times root x is x, so that's that. On the bottom, I just left it. And then I have a fraction over a fraction, so I flip it, I do the reciprocal. The x squared, the -1 over x squared just flips up, put a negative out front. One of the x's cancels, so I'm left with a negative, an x on top, and a 2 on the bottom. Then I'll let x go to 0, so 0 over 2 is 0. So we finally get natural log of y is 0. I want to get y by itself, so I take e on both sides. And this time, instead of e to the 1, I get e to the 0. And e to the 0, well, any number to the 0 is 1. So we get 1. So our answer is 1. What do you think?
When we go, can we go back up to where you have L and Y equals the limit of x approaches 0, 1 over 2x over -1 over x squared?
Yeah, what about this?
Let me see, the next one down.
Uh-huh.
So when we move down one more, I'm confused on.
All I did was I said, instead of dividing this fraction, I'm going to multiply by the reciprocal, like that, right?
Okay.
And then I went straight across. That gives me the x squared. And the negative, I just put it out in front of everything. So
Okay.
x squared and then the 2x on the bottom. Is that okay?
Yes, thank you.
Okay, good. Uh-huh. And then one of the x's cancels, and then we're pretty much from there, we're kind of home free. Okay. So that's it. That's it for L'Hopital. We've spent a day and almost a half on this, and that's because it is a very important section for any future math that you're going to do, whether it be Cal 2 or differential equations or anytime you're trying to find out the behavior of numbers in a limit. The L'Hopital is a very, very powerful and useful technique. All right. Okay, we still have some time, so I have enough time to at least introduce the next topic. We are going to move into the next chapter. Actually, we are into chapter 4, which is applications of differentiation. And the good part about this first section is that it's very visual. So I can just kind of go through these notes pretty quickly, and I have enough time to at least get us to a point where we can start maybe talking about a problem in this section. So there's lots of applications for differentiation. Okay, there's a ton of things you can do now that you know how to take derivatives. The book, chapter 4, covers some of those applications. The first thing we're going to talk about are maximum and minimum values. And this, I would say by far, is the fundamental foundational thing when it comes to derivatives. Like, what was our end game goal of being able to do differentiation? Like, what is it that this was going to lead us into? And this is it, finding the maximum and minimum values of a function. And that's the first section. So we start here. So before we can even start, we need to get some definitions in place, some language. And these notes are all in Canvas, so I don't expect you to copy this all down right now. So I'm only going to highlight the things that I think are important, and you can go back and look at these on your own time. The first thing is this thing called the absolute maximum value of a function. So let's say you have a function, you have a graph, it might go up and down. The absolute maximum value of the function would be the highest point on the graph. Okay, it's the absolute highest maximum point on the graph. The absolute minimum value would be the lowest point on the graph. All right. In either case, whether or not you're looking at a absolute maximum or minimum, we call those either absolute maxes, absolute mins. You might hear me say global max or global min. Global meaning on the entire domain of the function, that's the global maximum, the highest point. That's absolute max, global max, same thing. Global min, same idea. It's the lowest point on the graph. In either case, all right, whether or not we're talking about an absolute max or min, these are called extreme values of the function. So if I say, hey, go find the extreme values of this function, then what I'm telling you to do is go find me the absolute maximum and absolute minimum. All right. Now, we can have absolute maximums and minimums, but we can also have these things called local maximums and minimums. So local maximums and minimums are a little bit tougher to understand because local means that, let's say we have a graph that does this. This point right here would be the global maximum, because that's the highest point on the whole graph, isn't it? This point in black would be referred to as a local maximum. It's not the highest point on the graph, but locally it is. It's kind of like this point is like the king of the hill, but only this hill, right? This point's a king of a hill, but it's the king of this hill and it's the king of all hills, if that makes sense. The global maximum versus the local. Now, the blue point is also a local maximum. Local just means that you're the highest point in this little neighborhood, right? So in this picture, we actually have two local maximums and one global maximum. Make sense?
Yes.
Minimum works the same way. Say again?
Didn't we do this type of stuff in algebra? To find
I don't know.
the maximums and stuff like that?
Yeah, you probably did talk about it. You probably did talk about it, yeah. Now, what about this point? I guess I have to use black again. What about this point right here? I'll put an X on it. What about that point? What do you think that point would be referred to as?
Local minimum.
A local minimum. It's like the lowest point in its little neighborhood. Do y'all agree?
Yes.
Locally, it's the smallest point. Now, does this graph that I drew have a global minimum?
Okay.
No.
Look at the arrows I drew here. These arrows imply that this just keeps going down forever, right? So that would imply that there is no lowest point on the graph. The graph just keeps going down forever and ever and ever. So this would not have, this particular graph would not have a global minimum. It appears to have a global max, but not a global minimum. Understand? We're going to do more visualization. I'm just trying to first get the ideas out here.
So
Okay. Yeah.
so like we'll kind of always have a local and global maximum, but it's not guaranteed about a minimum because it can be infinite.
No, you're never guaranteed anything at all. You're never guaranteed a global anything. You're never guaranteed a local anything. It's just when you look at a graph, sometimes you have these things, sometimes you don't. I mean, just think about this graph right here. Just a flat line. This doesn't really have a highest value. Although, let's say it goes through right here. Let's say that that's 3. Okay, 1, 2, 3. Let's say that that's 3 right there. You could argue that the global maximum of this function is 3, right? Because 3 would be like the highest point on the graph. But you could also argue that 3 is the global minimum because it's also the lowest point on the graph, right? But it doesn't have any locals anywhere either because there's no like hills or valleys. So you're not always guaranteed to have them, okay? But when we do have them, we can call them something. So look at this right here. Look at this graph. Okay, now notice that this graph, I start it somewhere and then I stop it somewhere. So this graph, we're only looking on it on a closed interval, right? If we were to imagine moving along this curve, right, from left to right, when we get to this bottom right here, that would be a local what? Minimum. This would be up here.
Maximum.
Local maximum. Down here.
Local minimum.
Local minimum, right? So we have local min, local max up here, local min. So let's show those local values. There they are, okay? Now, what about global? What about global?
First local minimum would be the global minimum.
Those 2 points right there in green, here. That's the global max. That's the highest point. If you look, that's the highest point on the graph. And this is the lowest point on the graph, right? Look at this picture. Let's look at our locals first. Those are local max mins, right? Here's a local minimum, local maximum, local minimum. What about the global? Be careful here. Look at the global. Here are the global max and mins. Look at the global minimum is this point because it's the lowest point on the graph, right? But do you see how this is the global maximum? And that's not on like a hill, right? It's not on a hill. It's just the highest point of the graph on this interval. So it's happening at one of the endpoints. Y'all see that? How about this one? Oh, I've already done this one. Oops, sorry. So this one, local, right? There's your local. And oh, there's something on here that's, I have to add here. The
dots.
Those are arrows, okay, that go up forever. So this time we're not on a closed interval anymore. It just keeps going. So here's our locals, right? Local min, local max, local min. How about global? We have a global minimum right here, smallest, lowest point on the graph, but there is no global maximum because it goes up forever. Do y'all see this as being a pretty clear idea? There's not like anything crazy here. It's pretty easy to look at a graph and be able to identify these things.
Yes.
Is that fair to say?
Yes, sir.
Man, sorry, these weren't supposed to be here. Let me do something. Evaluate the notebook, set it all up again. Okay, here we go. So this one we have. I'm waiting for my computer to catch up. Hold on.
There are two global maxes and minimums.
Yeah, there we go. Okay, so look, here's our locals. Local min, local max, local min. Global, I actually have 2 points that are the highest points, right? And I have 2 points that are the lowest. So sometimes people think, okay, the global max, you can only achieve the global maximum at 1 point. But in fact, you actually could have more than 1 point where you have a global max. Just think about the sine function, right?
Yeah.
You know, if you take like the sine like that, you have like global max. Those are all local maxes, but they're also global maxes, right? And then these are all local min, but it's also global min, right? Because they're all the lowest points.
So our global maxes are also going to be global minimum? I mean, local minimums? Like, are they gonna be included in the local as well?
For the most part, yes. Every global max that we've had has been a local max, except at the endpoints. And that's kind of debatable. Some people call endpoints local maxes too. For us, all we want to do right now is to understand visually, like connect the idea of a global and local to the visual part.
Okay.
Okay, so now we have a very important theorem, and I think that's where I'm going to start next class, right there. We have the basic idea. What we're going to be doing, if you look back at all of these, okay, if you look at all these pictures I drew, what you'll notice is that at every point that we ever had a local max or min, the slope of the tangent line there is 0. Do you agree?
Yeah.
And that means if I ever give you a function and I want us to go find the local maxes and mins, then what you're going to be doing is trying to figure out where is the derivative 0, right? If you could figure out where the derivative is 0, then you'd be able to tell me the x values that these occur at. I'll give you a real simple example. I know we've got to go here. If you take this basic parabola, f of x equals x squared, and we wanted to figure out where we had this right there, right? Like we asked, at what x value is that happening that we have the local minimum? Well, that's where the tangent line is 0, isn't it? So let's take the derivative of this. What's the derivative of that? 2x, right? And let's set it equal to 0. And if you solve this for x, you get 0. And so that's telling me that at x equals 0, something interesting is happening. It looks like that's where I have something locally happening. I don't know if it's a local max or min, but something is interesting there. So up to this point, everything we've done, we've been taking derivatives, right? Raw derivatives, raw derivatives, raw derivatives. And I've held off on the algebra as long as I possibly can. But from this point forward, we are going to be setting derivatives equal to 0. That's what a lot of the next sections are going to be. Take the derivative, set it to 0. Take the derivative, set it to 0. And that means we're going to be having to take those raw derivatives and work with them algebraically. So that could be problematic. You know, that's usually the thing that students have a problem with. They don't have a problem with the derivative. They have a problem with setting it equal to 0 and solving it. So we'll get into that, okay? Everyone have a great day.
Okay then. Sorry about all of the noise and stuff. I really didn't know what was going on. I really didn't.
Well, I only booted you out because I was trying to mute you and it wouldn't mute you. So I was still hearing this weird like computer sound and I couldn't stop it and everyone could hear it. So I just decided to just kind of remove you from the session. Did it not let you back in?
I was trying to get in. It was just a whole mess because I left as well. So if you kicked me out, I also left. So like, I don't know what happened. And then I was trying to get in and I don't know what was going on. I was using the app because of whatever. I don't know. It was just a hot ass mess. And I just feel really bad for all the noises and everything that happened.
It's all good.
So I'm sorry about that. I really didn't mean
No
that.
problem.
And thank you. Also, I had a dream about the local max and minimums yesterday. I don't know why I did, but
It's a nightmare then, right?
I was like, the intermediate value theorem is blah 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 blah. Like in my sleep, I was like, what? Okay.
All right. Well, I've got to run today, so y'all take care.
Thank you. You too. You have a good day. Bye bye.
Bye-bye.
Can I ask a quick question?
Yeah. What's up?